All right, let's get started with lesson 5, free energy and equilibrium. In this particular lesson, we are going to learn how free energy, delta G, is related to the equilibrium constant Kc. If we know the value of delta G, the free energy value, we are able to determine if the system has reached equilibrium or if the forward or reverse reaction is dominating. For instance, if delta G has a negative value, then the reaction is going to proceed in the forward direction, and we will have equilibrium mixtures of a higher proportion of products. Negative delta G favors the forward reaction. A positive delta G, on the other hand, is going to favor the reverse or the backwards reaction, and the reaction is going to proceed in the backwards direction, and we'll have an equilibrium mixture that is predominantly reactants. But if delta G is 0, then the reaction is already currently at equilibrium, and the system has its highest possible entropy value. All right. Now here's an equation that relates delta G with the equilibrium constant. You do not need to memorize this equation, but you certainly need to be very familiar with it and know how to use it to solve problems. In this equation, we can either solve for the delta G value if we know what the equilibrium constant expression is, or we can solve for Kc if we know what the delta G value for this reaction. Now, I need to modify something with this equation. We need to actually add a negative sign in front of our t. So it really should be, the equation should be delta G naught standard conditions is equal to negative RT times the natural log of the equilibrium constant Kc. All right, so I forgot to insert the negative, so just do that. All right, so we already know what delta G is. That's the standard free energy change of the reaction. R is the familiar gas law constant of 8.31 joules per Kelvin per mole. Now I want to make note that the units of R are in joules, where usually the units of delta G is in kilojoules. So that's something we have to take in account of when we're solving in this equation. T is the absolute temperature in Kelvin, and then of course ln Kc is the natural log of the equilibrium constant. Okay, so let's go ahead and do a couple of practice problems that involve using this equation. So example problem 1, A, calculate the delta G for the following reaction, and B, what is the value of the equilibrium constant at 298, and C, is the reaction spontaneous at 298 Kelvin. Okay, so in order to find the value of delta G, we are going to have to use some delta G formation values that are listed here. All right, so we're going to use, for A, we're going to use this equation. Delta G is equal to the sum of the delta G of formation of the products minus the sum of the delta G of formation of the reactants. This equation you should be familiar with. Okay, so we're going to take the products minus the reactants. So if we set this up, then delta G naught should equal 129.7. That's the value of our product, minus 209.2. And since we have 2 moles of reactant, we're going to have to multiply that by 3. That should give us a value of negative 497.9 kilojoules. Okay, so there's our delta G value for A. Now for B, we need to find the Kc value. So this is where we're going to actually use our equation, delta G equals a negative RT natural log of the Kc. And we're going to have to find Kc. Now, remember we have units of kilojoules where R is in joules. So what I'm going to do is I'm going to go ahead and divide this by 1,000 to get it into joules in order to find our Kc value. Okay, so we're going to plug this in, and I should have then actually not divide, take that back, I need to multiply. Need to multiply this by 1,000. All right, so then get to get it in joules, right? So that would leave us with a negative 4979 joules is equal to negative R, which is 8.31 joules per mole Kelvin. Okay, we're going to multiply that all by the temperature, which is 298 Kelvin. And then the natural log of Kc, which we don't know. All right, so when we do the math, we should find that we end up getting a positive 200.9 is equal to the natural log of Kc. So now, in order to find Kc at this point, we have to take the inverse log of Kc. To find the inverse log, you need to take, find your natural log button on your calculator, and usually above there, there's an EX button. That EX button is the inverse log of the natural log. So it'd be, see, you're going to just put in E, and then you're going to put in 200.9 into your calculator, and that should give us a value of 1.78 times 10 to the 87. All right, so what we're saying here is that the Kc value for this reaction should be 1.78 times 10 to the 87. All right, really large K value. All right, this really tells us that the reaction predominates with the products at equilibrium. And the forward direction is definitely favorable. And the fact that we got a negative delta G also tells us that it is going to be spontaneous in the forward direction. And the forward direction is going to be favorable. Okay? So there's how we do essentially a problem using that delta G, our delta G equation here. All right, let's move on. Okay, example problem 2. We're going to calculate the delta G. This should be delta G naught for the following reaction where we have temperature and, we're given the Kb value. Now the Kb value is the Kc, all right? So sometimes we change the Kc value to another letter to indicate what type of reaction it is. In this case, this is a base reaction, and so therefore we call it the equilibrium constant for a base, Kb. So Kb and Kc are the same thing, all right? So here's our, we have our reaction, and what we're going to do is we're going to use our equation, delta G naught is equal to negative RT ln Kb in this case, okay? And we already know what Kb is, so we just need to find delta G. So delta G naught is equal to negative 8.31 times 298 Kelvin, that's our temperature, times the natural log of 1.8 times 10 to the minus 5, right? So when you do all the math, you multiply here, you multiply the natural log of 1.8 times 10 to the minus 5, we get a delta G value of 27.072.5 joules, okay? Because remember, we'll get it in joules because our R value is in joules. So then I'm going to now divide this by 1,000, and that's going to basically give me 27 kilojoules. And that will be my answer. So it's a positive 27 kilojoules. So what that tells me is that this reaction is not very spontaneous in the forward direction. And that's indicated by our Kb value. Our K value, our equilibrium constant value, is really small, which tells us that the reactants are going to be favored and the reverse direction is going to be the favorable reaction. And that also indicates by our delta G value that the reverse reaction is more favorable than the forward reaction. All right? So that's how delta G and the equilibrium constant are related through this equation. Again, don't need to memorize it, but you do need to know how to use it. Okay? This last problem we're not going to do. We're not going to worry about. So that is it for now. Make sure, again, you're familiar with using that equation. Understand that if delta G is negative, it's spontaneous in the forward direction. If delta G is positive, it's spontaneous in the reverse direction. If delta G is 0, then we are already at equilibrium. All right, and that is it.